We're going to end with two um, big ideas: contingency tables and probability trees. Okay, um, so what are these all about? The contingency table, I think these are both awesome, but they're on another level of thinking from what we've done before, and definitely different than the things we've done before. And they really model statistics. They probably are a lot closer to what we think of as statistics than what we've been doing so far. Okay, so contingency tables. We're just going to jump right into practice problem 12. The best way to introduce this is with an example. It says, are married people happy? The table below shows results from the 2002 General Social Survey. All right, so we have this big table, and you can see there's a lot of categories. So across the top, very happy, pretty happy, or not happy. They're talking to all married people here. And then the totals on the side, and then down the rows are male, female, and then some totals there. So what I like to do in a typical class meeting is to say, just kind of like test the class, like, all right, just looking at that, could you tell me how many males are pretty happy in their marriage? How many males are pretty happy? And usually people, they understand how to read this table. So how many pretty happy males are there? 95, right? How many total females are there? How many total females? And it's 278, right? The total of the females on the right side, 278. Okay, so we can kind of see how many very happy males there are, how many very happy females, and pretty happy, right, of each of the different groups and how they are split up. And then we get totals all around the outside. So how many total very happies are there? 370, right? Hey, here's a good question. How many total married people took part in this survey? How many total married people in this survey? And that's in the lower right. 603 is all the number of people that participate in this survey. Okay. By the way, I'll just share this a little bit with you guys. Are married people happy? So I got married in my 30s. I got married when I was 33 myself. And I got to say, being married, far, far happier than when I was single. Far happier. And I was a happy single guy. But being married, far better. Now, with that, there's a big price to pay. It does not come without a price. Life is definitely harder. There's no question about it. And there are times when, you definitely don't feel happy because you got a lot to work through, especially in that first year of marriage. If a lot of you guys are single, ladies single. However, it's worth it. Push through that because, when we say happy, we mean like content, or fulfilled. Life is much more fulfilling being married, but there's a price to pay. And then when you have kids, even more fulfilling. But now there's an even heavier price to pay, way heavier than even being married, which was a big one, which was really heavy on itself. Okay. Actually, when I got married, I had kids right away because I have two stepkids. My two girls are my stepdaughters. So I got married and had kids immediately. Um, so I think I'm a bit of an authority. Now that said, don't get married to become happy. It doesn't work like that. You got to be content in singleness. Being married is not going to make you happy. If you get married to be happy, you're going to be more miserable than before. Don't do that. You got to be content in your singleness. Then that's a good sign that if you were able to be married, that you could pay that heavy cost. Okay, all right, let's get back to the question. So we see that that table there, the contingency table. Now let's go through these questions. We got a bunch. So part A, what is the probability that a randomly chosen married person is female and very happy? So we're going to see these ands, and we're going to see, the given, and that stuff is going to come up the or. What's the probability that a randomly selected married person is female and very happy? Okay, so we'll start with the most straightforward one. Well, looking at the table, how many very happy females are there? How many very happy females? You say, well, there are 149 very happy females. So I'm actually going to go back, and you see it there on the page. Let's put out all of the probability female and very happy. Let's write it all out. There are 149. Out of how many? Out of all the people that did the survey, right? 603. And I just erased the answer, 149 out of 603. And we're gonna round this to 3 decimal places. I think that'll be good. 0.247. Out of all the people that took the survey, the chances that any randomly selected person is a very happy female is 0.247. Okay. Hopefully that makes sense. Part B, what is the probability that a married person is very happy? Now, everybody who took the survey is married. So the probability that a married person is very happy. So what should we do? And well, you see the answer here, but let me go back and show you the notation as well. So we're just thinking probability of very happy, because everybody's married. So we're thinking, all right, how many very happy people are there? 370. All right. And we're going to divide that by the total, the 603. So 370 divided by 603, 0.614. How many very happy people in this survey? 370 out of 603. Okay. In part C, we get to the or. What is the probability that a married person is female or very happy? Okay, hey, now I wrote it out. Great. Kind of came to my senses here. The probability that a married person is female or very happy. All right, now it starts to get a little bit trickier for sure. We're going to use the formula for the or. So probability of female or very happy would be probability of female plus probability of very happy. But now we've counted the very happy females twice, so we need to subtract probability of female and very happy. Okay. Well, let's take a look at each one of these. Actually, notice we have this value already, and we even did this one already. So this is the only new thing to find, the probability of being female. And I went ahead and used the fractions to minimize the rounding error. The females, how many females are there? 278 out of 603. What are the chances of being very happy, male or female? It was the 370 out of 603. And now we've double counted the very happy females, so we need to subtract female and very happy, and that's what we did back here, 149 out of 603. So we can put all of those together since they all have the same denominator. And it turns out that 278 plus 370 minus 149, put all the numerators together, and you get 499 out of 603. Which in this one gives a final answer of 0.828 when you round. Okay. So say they go in and they just randomly select one person who took this, chances of them being female or very happy or both, 0.828. Part D, what do we have? What is the probability that a married person is female given they are very happy? Okay, here's the given. Let's see what's going on with this. The probability that a married person is female given they are very happy. So we've got this formula. Probability of being female given very happy. So if we go back to the formula for the given, this would mean probability female and very happy, right? We take both, divided by, and remember, think of this like a division symbol, divided by the probability of being very happy. So what's happening is we're only looking at the very happy people. Out of the very happy people, let me back up. Out of the very happy people, how many of them are female? Like, what's the chances of them, of a randomly selected person being female? Okay. So from here, what do? Well, actually, we know both of these numbers from some previous problems, so that's really nice. The female and very happy was 149 over 603. The probability of being very happy was 370 out of 603. And so we've got fractions within a larger fraction here. Now, you may remember what to do with fractions in this situation. You may not, so I'll walk through it. If you have a fraction over a fraction, what you do is keep the fraction on top as it is, but the one on bottom gets flipped over and multiplied. We call it the reciprocal. So 370 over 603 becomes 603 over 370, but then that division changes to multiply. From there, we notice, hey, the 603s cancel out, and so it's 149 over 370, and we got our answer. We can divide those. We could have divided back here. Be careful if you do that, though. You need parentheses. If you go for it right there, you need parentheses like that. Or you could remember flip multiply. Actually, I think there's a better way to think of this problem and even go directly from your formula here to the 149 over 370. You see both of those numbers in the chart, right? The 149 is the very happy females, and the 370 is the total number of very happies. What you could do is think of this, what are the chances of being female given they are very happy? What you could do is say, okay, I know we're only considering the very happy people, right? That's already occurred. We know we're only talking or only choosing from the very happies. So what are the chances that we get a female? Well, 149 out of 370. It's like, how many females are there divided by the total number of very happies? Or how many very happy females are there divided by the total number of very happies? And there you go. So 0.403, however you get it, 0.403. Okay. Let's continue with number 13. Now, number 13, we're going to create one of these tables ourselves to answer the question. So I think this is really cool. It's a lot of fun when they're created for us, but even better when we get to do them. All right, so 13 says, say 13% of students are computer science majors. We're going to call that event A. Being a computer science major, event A. 15% have taken discrete mathematics. We're going to call that event B. Discrete mathematics is a course that any computer science major would have to take, but a lot of other people take it too. It's a high-level math class. Okay, and 84% of students are not computer science majors and have not taken discrete mathematics. And so we get to the question, what is the probability that a student is not a computer science major but has taken discrete mathematics? And it turns out with just the information they gave us, we're going to be able to answer that question. And, you know, for the moment, it seems like that's impossible. I mean, sure, they gave us a couple percentages, but how can I possibly make sense of it to the degree where I can answer what's the probability that a student is not a computer science major but has taken this class? But they actually gave us just enough where we can figure it out. So it says, before trying to answer, consider if a contingency table would help. So that's how we're going to start. We're going to make our table, and we're going to piece all this together. And once we do that, once we have the table, the answer to the question is going to be just right there for us. Okay, so you notice number 13, I've got it set up as the probability of A complement and B. So why is that? Well, they said, what's the probability that a student is not a computer science major? Well, if computer science major is event A, then not a computer science major is A complement. But they have taken the class. So A complement and B. Okay. Here's what I'm going to do. Here's going to be the look of our contingency table. We're going to set up, well, I guess you could say 4 columns and 4 rows. So these, say maybe these 3, rows and columns, or the rows and columns will represent A complement, B complement, and then we need totals on the sides like this. Of course, you could reverse where the A and the B and the A complement and the B complement go. I decided to make the A the rows and the B's the columns. And you see I've had some numbers there and I've erased them. Pretend like you can't read that for the moment. Okay, so we're going to start to fill in our table. So let's go back to the beginning of the problem. Say 13% of students are computer science majors. Where would we put the 13%? And this would be a lot easier if we were all in class together, right? 13% are event A. Well, they didn't mention event B at all, right? So that's the total of event A. 13% have satisfied event A. 15% have taken discrete mathematics. So where would we put 0.15? Well, discrete mathematics is event B, and it's the total. Okay. And then they tell us one more piece. 84% of students are not computer science majors and have not taken discrete mathematics. What did they just describe to us? They're not this major and they have not taken the class. So that's an and, so that means, you're right, they're talking about both of those things have occurred. Where would we put the 0.84? In the A complement and B complement square. They are not this major and they have not taken this class. 0.84. Most students, you can imagine, would be neither of these things. Okay. It turns out there is one more square that we can fill in that does not need to be mentioned. And it's the total of totals. This is 1, or you might even fill in 1.00 like 100%. The total of the totals is going to be everybody, at this university or college or whatever it is, 100% of the students when you add everybody up. So with just this information, we can